Okay, so these are the examples for the last topic, wattmeter or power measurement using wattmeters. So we'll have um, around four examples for three-phase balanced load and another two for the still under wattmeter or power measurement, but we'll focus on the other type of load, which is the unbalanced load. Okay, so the first example, okay, so we have here two wattmeter method, no, so it's being used to measure power taken by a delta connected load. Okay, so the wattmeters read. Okay, so that's we assume, no, so the first one to be wattmeter one. Okay, so we have here wattmeter one. Okay, so and another reading 500 watts. Okay, so for wattmeter two. So the line voltage is 120 volts. So we are asked to identify, okay, so the following. So the active power, the reactive, the apparent power, the current drawn, and the okay. So the impedance, no, so the impedance per phase. Okay, so first, no, for the active power, so we are given. So these are the okay. So given data. So the line voltage is given to be 120 volts. Wattmeter 1, that is 1500 watts. Wattmeter 2, so that is 500. Okay. For the active power, now so P, so from the previous discussion, so the total power drawn using 2 wattmeter is equivalent to the reading. No? So the sum of the reading, okay, so that is P, that is 1500 plus 500. So that would be 2000 watts. Okay. And for the second item, so we have there the reactive power, V. So Q is then equal to square root of 3. Okay, so multiplied by wattmeter 2 minus wattmeter 1. Okay, so Q then, so that is square root of 3. Okay, so that's 500 minus 1500. So this gives us Q equals to, okay, so that's negative 1732. Okay, so unit in var. So, okay. So since the reactive power is negative, okay, as you can see, no? So the negative reactive power. So this means that the load is capacitive. Okay, so we didn't say, no? We didn't say that if wattmeter 1 is greater than, okay, so wattmeter 2, Okay, just like in this case, no? So watt meter 1 greater than watt meter 2, then you have their leading power factor, watt meter 1 less than watt meter 2. So you have their lagging power factor. And if watt meter 1 equals to watt meter 2, okay, so we have their um, purely resistive. Okay, so if watt meter 1 is equal to watt meter 2, then therefore Q is 0. Okay, and okay, for letter C, okay, so the apparent power S. So S can be calculated using no, so the formula P square plus Q square. Okay, so this is equivalent to uh, the square root of, so 2000 plus 1732 square. Now, so this gives us, okay, so this gives us 2645.7 VA. Okay, so or another way is to use no, so the formula S is equal to power over the power factor. Okay, so wherein you can calculate no, for the power factor to be, so that is using the formula no, so derived last time, square root of 3. Okay, so square root of 3. Okay, so multiplied by the difference, no? So that's watt meter 2 minus watt meter 1. Okay, divided by watt meter 2 plus watt meter 1. Okay, so that's plus 500. Okay, so this means absolute. Okay, so that means you ignore no, so the negative uh, part no, of the answer. Okay, so that is equal to, okay, so by calculating directly, okay, so by the way, this is theta, no? So this isn't yet the power factor. Okay, so this is theta. Okay, so that's theta that is equal to uh, okay, so such that the power factor can be calculated as cosine of theta, that is, okay, so if you take cosine of this one, so the answer is 0.7 uh, okay, 0.756. Okay, so and then if we substitute, no, so we have here 2000 divided by 0.756. 56. So that would be, okay, so that's 2645, no? So zero point 0.5 VA. So that's the same, no? So as with the previous calculation. So do not worry with the last or the decimal part, no? So it actually matters in the rounding off, no? So that's the same, no? So as with this one. Okay, so and next is the current drone, no? So for the current drone, okay, so we can uh, perhaps erase this part here, no? So okay, so for the current drone, we can calculate the current I. Okay, so this is for letter D. Okay, so recall the formula power is equal to square root of 3. Okay, so that's VL, IL, and cosine of theta, no, or the power factor. So uh, power is equal to 2000, no, 2000 watts. Square root of 3, you have the 120. IL is unknown, and then 0.56. Okay, so IL would be, okay, so we have here 12.73. Okay, so this would be the current drone. Okay, and okay, so okay, so we can calculate, no, for letter E, so which is the impedance, no? So okay, never mind the magnitude, no? So we'll just calculate, no, the complex expression of the impedance per phase, okay, of the delta connected load. Okay, so for letter E, okay, so that's okay, so uh, first is, okay, so the expression for the impedance is given by this one, no? So capacitive impedance, no? So we can have R minus JXC. So we can calculate for we can calculate first, no, for the value of R. Okay, so given the current, so we can have power that's 3. Okay, so that's 3 IP, no, square multiplied by R. So as we all know, no, current or the power is given as 200 watts. That's 3. But for IP, okay, so take note that this is a delta connected load, no? So the expression for IP is equal to 12.73 over square root of 3. Okay, so take note for delta. Okay, so your IP is equal to IL over square root of 3. Okay, so multiplied by R. Okay, so you can calculate R by, okay, 2000 divided by, okay, 3. Okay, so that's 90.7. Okay, so to calculate for the other parameter, okay, let's say the reactance, no? So you can solve for the reactance, no? So using the impedance triangle, so this is theta, Z, R, and XC. Okay, so you can solve for XC, no? XC, um, so you have the tangent of theta, for which is 40.89. So that is XC over R, no? So okay, so you may calculate now XC, no? So XC can be calculated as 90.7 tangent of 40.89. Okay, so XC then is equal to, okay, 78.53 ohms. Okay, so such that the impedance would be, okay, so the impedance would be uh, Z, so that's 90.7 minus J, 78.54. That would be in ohms. Okay, so this is for, okay, so item or example number 1. Okay, so example number 1 is for balance, no? So balance three-phase load. And okay, for example number 2, okay, so okay, example number 2, so you have the Y connected load, no? Balanced Y connected load. Okay, so with impedance of 8.66, no? Plus J5, okay, ohms, no? Connected in Y. So line to line voltage is given to be 300 volts, no? So 300 plus J0, or basically 300 volts. So according to the problem, no, so we have a wattmeter connected with its current coil in uh, okay. So the wattmeter is connected in the circuit, no, so with its current coil in, okay, so okay, with its current coil on okay, so that would be line B, and potential coil on A and C. Okay, so the problem is now, so we have a Y connected load balance, not so and then a wattmeter now is connected in the system. So with the current coil in line B and the potential coil now on A and C. So we are asked to calculate also the reading, the wattmeter. Okay. So first we need to uh, draw no so the given circuit. So we have actually Y connected circuit balance. No, so that's okay. So you have there 300 volts, no, as given. Okay, so impedance per phase, that's 8.66, no, plus J5. So the same also with the other phases, no, J5. So this would be line A, line B, and line C. It's mentioned, no, so the wattmeter. Okay, so the current coil is in line B, whereas the potential coil, no, so that's in A and C. Okay, so this would be the wattmeter position of the wattmeter, no. So we try to work out with the reading of the wattmeter that is equal to, no. So the magnitude of voltage AC, the current IB, and cosine of theta VBC minus theta IB. Okay, so okay, so okay, so we need to identify, no, so the following parameters, no, which uh, the voltage and the of course the line current IB, no, so what we need, okay, for the voltage is the phasor of VAC, and for the current we only need also to calculate for IB. So while the rest, we may opt not to calculate them because they are not, or those values no cannot be used no so in the problem. So for IB, as you can see, no, that's IBN. That's the same, no, so as with the line current IB because it's a Y connected load. Okay, so now, first is we need to plot also the phasor of the okay, so the line voltage first. Okay, so first one is to a plot. Okay, so you have there VAB. Now, assuming positive sequence, that would be V. Okay, CA, and then that would be VBC. Okay, so since it is a Y connected load, so we can have okay we can have no so the per phase no voltage. Okay, so phase source no, so this would be V CN, so it lags by 30. Okay, and then this would be VBN. Okay, so why do we need to plot no so the per phase voltage? So because we need, no, so the phasor of the per phase voltage VBN to calculate for the current IBN, no. So if we try to calculate IBN, that's actually VBN divided by the impedance Z, no. So wherein VBN, that is 300 over square root of 3, that would be angle, that's negative 150. Okay. So to take note, no, VP is equal to VL over square root of 3 for a Y connected load. So that's divided by 8.66 plus J5. Okay, so IBN then would be, okay, so that's 300 over square root of 3. Okay, negative 150 divided by, okay, that's 17.32 angle 179. 0.99, or shall we say, um, okay, that's 17.32 angle 180. Okay, unit in ampere. So basically, we can now identify, no? So by the way, VAC, no? So that's or that can be plotted, no? So opposite of VCA. Okay, so this is 30, and of course this is 60. No? So therefore, we can calculate, no? So the wattmeter reading to be 300, so that's the magnitude of VAC. The magnitude of IB is 17.32 cosine of, no? So that's the angle of V, okay, sorry, this is AC, no? So this VAC, that's negative 60. Okay, minus theta IB, no? So this is equivalent to IB. So that's 180. Okay, so that's wattmeter. That's okay. Let me calculate. 17.32 times cosine of 180. So we will have a reading of negative 2,598. So again, this only indicates, no, the reading of the wattmeter. That doesn't mean that the power drawn by the circuit is negative, no. Okay, so it is just an indication, no, of the wattmeter because of the positioning, no, of the current coil and the potential coil, no, of the wattmeter for the example. Okay, so and okay, for example number 3, so you have there two wattmeters, no? So that this is actually the same as with example number 1. Okay, so you have the two wattmeters used to measure, no? So the total power drawn by three-phase circuit. Okay, so take note, no, so of the statement. So the first wattmeter reads 4,800 watts, while the other wattmeter reads 400 watts after reversing its current coil. Okay, so meaning to say, wattmeter 1, that is equal to um, 4,800 watts, but uh, okay, but for wattmeter 2, so the reading is 400 watts, no? So after reversing its current coil. So therefore, so when the original position of the wattmeter 2 is uh, put back, okay, so the reading of the wattmeter 2 is equal to negative 400. Okay, so remember in the first video presentation given to you, so I explained there um, what will happen, no? So to our wattmeter when the current coil is reversed. So the wattmeter will still have the same number indication, but with a negative value. So meaning to say, the original reading of the wattmeter 2 is supposed to be negative 400, but when the coil is reversed, it becomes negative of the negative 400, which is 400. Okay, so therefore, the original reading of the wattmeter 2 is um, negative 400. Okay, so we are asked not to calculate um, the following, so the load power factor, the current, okay, and the impedance per phase, no. So let us say, let us say that the line voltage, in this problem is 208 volts. Okay, so you can calculate, so letter A, so that's the power factor. You can calculate that first, so that's tangent inverse, of square root of 3 times wattmeter 2 minus wattmeter 1. Okay, so that's 4,800 divided by wattmeter 1 plus wattmeter 2. Okay, so theta here, again, just take the absolute value. Okay, so times negative. Okay, so that's okay, 5,200 over 4,400. Okay, that's 63, no? 0.96. So the power factor then is equal to, okay, so you have there 0.439. Okay, so for letter B, so to calculate for the total current drawn, okay, so by the load, so we need to calculate for the total power, which is wattmeter 1 plus wattmeter 2, no? So the total power would be 4,400 watts. Okay, so such that we can calculate for the line current, that's 4,400 over square root of 3 times the voltage, no? So that's 208 the power factor 0.439. Okay, so that's 27, no? So 27.82. Okay, so that's ampere. Okay, so assuming, no? So let's say letter C, no? Assuming this is Y connected, okay, so we can calculate for the impedance, no? So Z then is equal to, okay, so we can calculate, no, for the impedance using Ohm's law. So this is another way to calculate for the impedance. So that's I equals to V over Z. No? So IEP, that's VP over Z. So we can have no Z that is VP. Okay, that's 208 over square root of 3 divided by IP, which is equivalent to 27.82. Okay, so this is equivalent to, okay, the magnitude of the impedance, that's 208 divided by square root of 3. Okay, so that's 4.32 ohms. No? So this is the magnitude of the impedance. No? So how do we write the complex form, no, of the impedance? So recall, so the impedance can be written as 4.32 angle. So this should be the power factor angle, which is also the same as with the impedance angle, but we have to write negative 4, okay, 63.96. Okay, so why negative? Because we have leading power factor, no? So again, no, so if uh, wattmeter 2 is wattmeter 1, no, so is greater than wattmeter 2 leading. Okay, so as discussed in the previous example, example number 1. And once you have their leading power factor, so the power factor angle sign in the impedance is negative. So this is one way of calculating, no? So uh, the impedance per phase. You can also use this one, this method, not to calculate impedance in example number 1. Okay, so okay, for the next example, so we have here a three-phase induction motor connected across, no, so a 220 volt three-phase source, no, so three-phase motor. Okay, so a motor is considered as a three-phase balanced load. So a wattmeter reads 600 watts, no? So when the current coil is in line 1 and its potential coil, no, across 1 and 2. So basically we are, okay. So, but if the potential coil, no, of the wattmeter is transferred to lines 2 and 3, so the reading of the wattmeter is the same. No? So calculate the current drawn by the motor. Okay, so to illustrate, we need to draw, no? So the given. So we have here a three-phase motor, no? So that is A, B, and C. And then for case 2, so three-phase motor. Okay, so this would be A, B, and C. Okay, so the line voltage, no? So this would be under case 1, and this would be case 2. Okay, so take note that the under case 1, case 2, we have the same motor, but then the positioning of the wattmeter changes. No? So as you can see in case 1, the potential or the current coil is in line 1. Okay, so this is the current coil of the wattmeter. No? And then the potential coil is in 1 and 2. Okay, so the potential coil, so this is connected in 1 and 2. So this wattmeter indicates 600 watts. Okay, and as mentioned in uh, situation 2, the same wattmeter, no? So the same wattmeter. So the current coil is in line 1, but the potential coil is given or repositioned to 2 and 3. 2 and 3, or basically B and C. No? So the wattmeter reads the same reading, 600 watts. Okay. So we are asked to obtain, no? So the uh, current drawn by the motor. Okay, so let's try to take a look at the case 1 scenario. No? So for case 1, the wattmeter reading is 600. So that is equal to the magnitude of the voltage VAB, the current IA, okay, and the power factor, no cosine, no, that, not the power factor, but the cosine of theta VAB minus theta IA. Okay, for wattmeter 2, so you have there 600. Okay, so that's VBC, no? So then the current IA, cosine of, okay, so that's theta VBC minus theta IA. Okay, now so we can plot, no? So we can plot the phasor. Okay, so of this one, so that's uh, assuming this is Y connected load. I mean the connection of the motor is Y. So you can have VAB, VBC, and this would be VCA. Okay, so this would be, let's say, AN, CN, and BN. Okay, so as we all know, that's 30 degrees. Now it lags by 30 degrees. Okay, and assuming, no, so assuming that the power factor, no, the let's say the current drawn by the motor, IA, IB, and IC, no, since we assume the motor to be Y connected. So the currents or the line currents, no? So these are also the same as with the per phase current. Okay, so assuming that it lags, no? Assuming that it has a lagging power factor of theta. Okay, so uh, okay, so we assume, no, that the current, no, so or the motor takes a lagging power factor, so it lags, no, so behind the um, per phase, no, voltage. So let's say IAN, so by an angle of theta, ICN by an angle of theta, and also you have their IBN, no, so by an angle of theta. Okay, so take note again, the power factor is the angle, no, power factor angle is the angle between VP and IP. Okay, so we can write, no, so the first, okay, so this would be equal to 600, so that is equal to 220 current IA cosine of 0 minus theta IA, no? So IA is equal to IAN, so that is minus 30 plus theta. Okay, so this is 30 plus theta. Okay, so we have here 600, that is equal to 220 IA cosine of negative 30 plus theta. Okay, so from your trigonometry, the cosine of a negative angle is equal to, okay, so a trigonometric identity, no? So cosine of negative A, so that is cosine of A. So meaning to say we can eliminate negative, no? So that's 600, that is 220 IA cosine of 30 plus theta. Okay. On the other hand, we have second case, not the 600, that is 220 IA, that's cosine of, no? So theta VBC, no? So that is negative 120 minus theta IA, no? So theta IA is uh, that's okay. We can have, by the way, no, so we can, this is actually negative, no, negative 30 minus theta supposedly. Okay, so we can just eliminate, we can make this positive. Okay, so anyway, we'll have, no, so still the same result, no, so that's cosine of 0 minus, so that's actually negative 30 minus theta, no. Okay, so negative of negative, that becomes positive. So still we will come out with this one. So that is minus, that's, okay, 120 minus negative 30 minus theta. No? So for IA, we can have 600, that is 220 IA cosine of, no, so that's actually this is equivalent to negative 90 Okay, that's negative 90 and okay, so plus theta. Okay, so we can erase. Okay, perhaps we can erase this one. So assuming we divide, no? So let's say this would be equation 2, this would be equation 2, this is equation 1. So we divide equation 1 by 2. So we have there 600 over 600. That's equal to 220 IA. And then cosine of 30 plus theta, no? And then divided by 220 IA cosine of negative 90 plus theta. Okay, so therefore we can cancel out 600. Okay, so we can cancel out 600, might as well, no? So 220 IA, and then we can have cosine of 30 plus theta, that is cosine of negative 90 plus theta. Okay, so since they are equal, okay, but uh, again, no, using the identity cosine of negative a, that is cosine of a. Okay, so we can rewrite this as cosine of 30 plus theta, that is cosine of negative of 90 minus theta. Okay, so and then okay, so we'll erase this one first. Okay, so uh, okay, so we can rewrite this as cosine of 30 plus theta, that is cosine of, no? So we can eliminate negative, so that is 90 minus theta. Okay, so therefore 30 plus theta is equal to 90 minus theta. Okay, so since they have both the same trigonometric function, so therefore uh, we can equate, no, so the two angles. Okay, so we can have 2 theta that is equal to 60 degrees, or theta that is equal to 30. Okay, so meaning to say this is 30. Okay. Uh, okay, and then we can calculate, no? So we can calculate now the, okay, so let me erase this first. So we can have equation 1, no? So that is 600, 220 IA cosine of that's 30 plus theta, and theta is 30, no? So IA then can be calculated as, okay, 600 divided by 220 divided by cosine of 60. So we can have 5.45 ampere. Okay. So if IA is 5.45 ampere, we can calculate, no? So uh, that is actually, no, so the question, no, being asked in the problem. Okay, so that's 5.45, no?